So my name is Bongjun. I'm happy to present my research work, optimization-directed compiler fuzzing for continuous translation validation. So the problem we want to solve is the correctness of compiler optimization. A wrong compiler optimization can silently change the meaning of your code, leading to miscompilation. This is a very serious issue because in this case, a compiler does not give you warning. A compiler does not give you crash, so you not notice something bad happened immediately. So it's crucial to guarantee the correctness of compiler optimization in the first place. So to give you the idea of what a miscompilation looks like, let's take an example. This is a source program. It divides a number by b and times b. And if a wrong optimization kicks in, it can cancel out b term, but we know this is a miscompilation because if we give an input 4 and 3, the source program would give result 3, and the target program would result 4. But by compilation, the semantics is supposed to be preserved. But the challenge here is the complexity of real-world compilers. A real-world compiler like LLVM has a really massive code base and is constantly evolving. There were more than 30,000 commits and from 1,000 of developers in 2024. And if you look at this graph, there are increasing number of optimization suggestions in LLVM. It means that more and more optimizations are getting added to LLVM compiler, and our job is to check the correctness of every single one. The current approach to solve this problem is to use translation validation. Translation validation checks if the source program and the target program are equivalent, and it's widely adopted in compiler community like LLVM. For example, if you want to add an optimization rule in LLVM, you have to give the TP proof in the PL, so there is no counterexample in the optimization. So if you have an optimizer with a source program, you'll get a target program by a compilation. And what TP does here, it checks the result of the source program and the target program, and they are equal for every possible input. So from the previous example, what TV does here is checks the equivalence of the source program and target program. It finds the counterexample automatically for you. But TV also have a limitation. It needs input program to find a miscompilation bug. So if you miss an input program to trigger the bug situation, you're going to miss the bug. So our idea is to design a directed fuzzer specifically effective for compiler optimization to automatically generate input programs. So our contribution is summarized as follows. We developed the first directed compiler fuzzer for LLVM and TurboFan. We reported 27 miscompilations in our benchmark, while other state-of-the-art compiler fuzzers failed. And we reported 56 LLVM bugs, and 22 are patched as of today. So this is our system overview. We start with compiler source code with target location and initial seeds. And through slicer, we get a slice control flow graph and call graph. And using the information, the seed scheduler realizes selective coverage feedback and focused mutation target. And finally, the targeted mutator and compiler optimizer generates optimized program with a mutated program. And with translation validation, we can automatically find miscompilation bugs. So the first step is to identifying the target optimization. The target identification process is inspired by our observation that optimization is typically consists of two parts. The first part is checking the optimization condition, and the second part is returns optimized code. And the target line here, because the directed fuzzer's job is to generate an input program that reaches the target. So target line is where optimization is actually triggered and returned. So for example, if there is an LLVM commit, there will be updated source code. You'll notice there is a part that checks the optimization condition, and there is a part that actually returns optimized code. And this is going to be our target line. And because optimization has a really simple pattern, just like I said, we can do automatic target line collection. Like we can just do simple string search with a simple Python script. We can collect all the lines that returns a new optimized instruction. Or we can just prompt engineer LLM to analyze the source code and collect all the interesting optimization triggering lines. The second part is to use the guided search strategy. Guided search strategy through slicer and seed scheduler. The slicer is for selective coverage feedback. Coverage feedback is an essential information to guide the fuzzer. And if you can imagine, if we only use the relevant program locations in the coverage, we can boost efficiency. So this, for example, this is a CFG of our optimizer. And this is going to be the seed pool of our directed fuzzer. And as you can notice, there is a red part and there's green part. In red part, there's no way to reach the target optimization, but in the green part, the blocks are reachable to the target optimization. And in the seed pool, there are going to be some input programs that covers the red part, but you can imagine the input program that covers the red part, the blocks are not reachable to target optimization, and this is going to waste the space in the seed pool. And there are going to be green programs that covers the green part in the CFG, and the covered blocks can reach to the target optimization, so we want to only keep the green part. So what we want to do here is to slice out, it increases the efficiency. What we want to do here is to slice out the red part in the CFG to only keep the green input programs in our seed pool. And seed scheduler uses distance metric. The basic idea of distance metric is assign distance to target values to nodes in the slice CFG. So this is the CFG that we got from the previous slicer. And we are going to assign distance 3 to the first block because this block is 3 blocks away from the target optimization block. And 2, 1, 0 because following the same logic. And what we want to do next is to generate more mutated programs for a closer seed. So for example, if a seed only covers the first part, because it has the greatest distance, we are going to generate only few input programs. And if a seed program covers all the part, and you can see it covers the block of the distance 0, we are going to generate more mutated programs. So what it does is that we are going to generate more input programs that actually triggering the target optimization more frequently. The last step is to use targeted mutation strategy through targeted mutator. So interesting observation we use here is that it's not just conventional fuzzing. The input is a program. So in conventional fuzzing, the input is a bit stream. Because it is a bit stream, it's really hard to analyze the structure of the input. It's just a sequence of 1 and 0s. But in compiler fuzzing, the input is a program. And because this is a program, it has really useful structures like control flow and def use we can use. And def use relation is extensively used in optimization. Because optimization typically checks the def use relation of a program to actually apply optimization rule. So for example, if we have this optimization rule, this optimization transforms a program from a source program that multiply by 2 to the c to a shift left by constant c. If ever this optimization rule is implemented in an optimizer, the first check is going to be to identifying the multiplication operator. And next check is going to identifying the first operand and check it is a variable x. And next, we are going to check the second operand is a power of 2. And finally, the optimization is going to return the optimized program. So using this observation, we can implement a really efficient strategy that finds the next mutation target. Let's say in the input program, there is an add instruction. And let's say mutator changed the add instruction to the multiplication instruction. And it's going to increase the coverage because the first check in the CFG was to identifying the multiplication operator. And if you look at closely the neighbor nodes, there is a X and Y nodes. And if you look at the CFG of our optimizer, the next check is about the nodes X and Y. So using this observation, if we mutate more the neighbor nodes, we are going to cover faster the next optimization condition checks. So let's move on to the evaluation section. Our Optimuzz framework consists of two parts. The first part is fuzzer, and the second part is a translation validator. For LLVM, we implemented our own fuzzer, and we used a Live2 translation validator. And we collected all the 24 miscompilation bugs for the past 3 years in the LLVM. And if it's detectable by a Live2 translation validator, and we compared the other state-of-the-art compiler fuzzer like Flux and AliveMutate. And for TurboFan, we implemented our strategies on the existing JavaScript engine fuzzer Fuzzly, and we used TurboTB translation validator, and we used the known miscompilation bugs appeared in TurboTB paper. And we compared our fuzzer to the naive Fuzzly. And we assessed effectiveness of our framework. It appeared it performed significantly better than other sort of fuzzers. It reproduced 23 cases, while other sort of fuzzers reproduced nothing within an hour. And for TurboFan, we reproduced 4 cases, while other fuzzers did not reproduce anything. And we did evaluation study on strategies effectiveness. On LLVM, we implemented 3 variants. The first variant is base. This is an undirected fuzzer without any strategy. It only has just mutator operator we implemented. So in the base case, only a few cases are reproduced. If you see the top line is at 60 because the timeout is at 60 minutes, it means that the reproduction has failed. And with guided search strategy, the effectiveness really improved. The reproduction time reduced a lot, and we reproduced a lot more cases. And with the targeted mutation, the reproduction time also reduced, and we reproduced 1 more case. And same thing for TurboFan. We implemented 3 variants. The base fuzzer did not reproduce anything. And with guided search strategy, it's significantly better. The reproduction time reduced also, and with targeted mutation, we produced 1 more case. And you can see the reproduction time reduced also. We applied Optimuzz to LLVM bug finding. Optimuzz appeared to be a really effective tool to find unknown miscompilations. We deployed Optimuzz in 2 different modes. The first mode is the continuous mode. We applied Optimuzz for every target in each LLVM update, and we applied Optimuzz in batch mode. We applied Optimuzz for all targets in the latest version of LLVM. So in continuous mode, we found 8 bugs from LLVM GitHub commits. So let me illustrate what we did. So from an LLVM GitHub commit, there will be an updated source code, and we analyzed as I described. And from the target line, we used Optimuzz to find miscompilation, and on with the same process. And in batch mode, we found 48 bugs from the latest version of LLVM. So for example, if there is a source code like instcombine select.c++, we analyze source code automatically to find the target lines, and we fed the target lines to Optimuzz 1 by 1, and finally found 48 bugs. So in summary, we developed the first directed compiler fuzzer using a continuous translation validation. We developed 2 strategies. The first one is guided search strategy with selective coverage feedback with distance metric. And the second one is the targeted mutation strategy that effectively find the next mutation target. And we also have a real-world impact. We reported 56 bugs to LLVM, and 22 are patched as of today. Thank you for listening. You can find more details in our website.
right, we have time for a couple of questions.
Hi, hello. Really cool work. I have a question. I see you have found some bugs in instcombine for new commits on instcombine. My understanding is that you're supposed to still have a live link to actually check that the optimization is correct or not. Does that mean that the problem, I mean, the bug you found was like the mismatch between the implementation of the optimization and the alive link that you have to check that it's actually correct?
So I missed the second question, sorry. The first question was to, so yeah, this framework depends on the translation validation tool we use, right? So for TurboFan, we use TurboTV, for LLVM, we use Alive. So it is kind of bound to the bugs that can be detectable by the translation validation tool of our choice. And you know, Alive tool is a bounded translation validation tool, so we can miss some loop related miscompilation. That is true.
Okay. I see. Thanks.
Hi. I noticed that you did say that in the PR.
Can you introduce yourself?
Hi, Hamir Abbasi from Kwon site. I did notice that the existing translation validation tool is already run in the PRs. So because of this, are you not selecting for bugs that would not have been caught by those translation validation tools in the first place? Specifically, did you try running this on commits that actually found bugs and those that didn't find bugs in the existing translation validation tools?
So the main limitation of how the translation validation is used today is that the human developers are writing their test cases to fit to the translation validation tool. So even if they're trying really hard to cover all the cases that optimization role covers, there were cases that they're missing. So our fuzzer is really excels at generating the missing parts of the optimization rule covers, and I remember many cases that we caught the bugs like that. Did I answer your question?
Yes, it does. Thank you. Okay, then let's thank you again for the great talk.